lecture number 5. Today we are going to be discussing quantifying temporal coherence. So before we get started, let's look at the concepts that we covered in lecture number 4. So in lecture number 4 we were discussing the generic question that we handle within second order coherence theory, and this generic question is essentially that if I have a field, then in that field how are the field vibrations at the point space-time point r1 t1 and r2 t2 are correlated. So that's the very generic question, and the quantity that actually quantifies it is this gamma function, the cross correlation function, which is the ensemble average of this quantity v star r1 t1 v r2 t2. So as part of studying this question, we looked at the necessary mathematical ingredients, and the first one among those is the stationarity, the concept of stationarity. Here we are discussing the concept of stationarity in time, but there can be similar concepts in space and angle as well. So stationarity means when the correlation function of all orders are independent of the origin of time, then it's called the stationary field, stationary signal, stationary process. Now usually it is very difficult to find the correlation functions of all the orders, so we in most cases we only deal with what's called wide sense stationarity, and in this one, as long as the mean and the correlation and the second order correlation function, as long as they are independent of the origin of time, then we call it wide sense stationary. So as part of this, the intensity will be, since it has to be independent of the origin of time, so it will be essentially independent of time. On the other hand, the second order correlation function, this gamma t1 t2, will then depend only on the time difference, since it has to be independent of the origin of time. So these we looked at in the last lecture. Also, in the remainder of this course, whenever we say stationarity, we mean wide sense stationarity. So I'm not going to, maybe I will not always use this term wide sense stationarity. Whenever we say stationarity, we basically mean wide sense stationarity. Okay. Now we also looked at that we can this correlation function that is in time, like t1 t2, one can also look at correlation function in space. For example, this w omega 1 omega 2, this is called the cross spectral density function. This basically represents the correlation in the frequency domain, and it is defined as this ensemble average of this quantity v star omega 1 and v omega 2. So this we'll see, this is a very useful quantity, and this we defined in the last class. So cross correlation function, this gamma t1 t2, this can actually be represented in terms of this quantity, which is the cross spectral density function, as a two-dimensional Fourier transform. Of course, if we invert it, then we represent this w in terms of this cross correlation function. So of course, this gamma and this w, they form a Fourier pair in the two-dimensional sense, and this is what's called the generalized Wiener-Khintchine theorem. And we saw that for a stationary process, this actually simplifies a lot, and we have this autocorrelation function and the spectral density, and they form a Fourier transform pair, and this is called the Wiener-Khintchine theorem. Okay, we also looked at the concept of time average. Time average is defined as, we have a signal, we integrate that over time from, so this would be minus t2 to minus t by 2 to t by 2 in the limit t going to infinity. And we also saw that for a stationary and ergodic process, the time average can actually replace the ensemble average. So this will have a lot of practical implication, will make things much very simple whenever we can have the stationary and ergodicity satisfied, and which we will see, in fact in today's lecture we'll see the use of it. And ergodicity, we also look at ergodicity, which is defined as this condition, and this essentially means that if in a finite time interval all the random fluctuations of a statistical process can be contained, then the process is kind of ergodic. So, and we saw then that if this process is stationary ergodic, the use is that we can replace the ensemble average by the time average. So these are the concepts we looked at in lecture in in the last lecture. So in today's lecture we are going to be we are going to be doing the quantifying temporal coherence or temporal correlation. So we go back to this interferometer that we started with last lecture, and the again the generic question in this context is that let's say we have a field r naught t and so we ask the question that in this field if what is the correlation between the field vibrations at two space point is the two time points that are separated by time separation tau. So one field point being at t1, the other one being at t2. So what is the correlation between them? In order to answer this question, one has to divide this field into two and then combine it in such a way that the resultant field has the component from some field at t minus t1 and field at t minus t2. So these two field points are then separated by time t1 t2 minus t1. So that's this is the generic methodology for kind of answering this correlation type question. Okay, so now in today's lecture we are only going to be looking at this the temporal effect. So I will remove this spatial labeling to make things simpler. So we can write this one as Vt as k1 Vt minus t1 plus k2 Vt minus t2. So it's just same. So just that the signal here in time at time t has component from fields that are separated by t2 minus t1, and that is precisely what we were after. Okay, so since this is the field V, we know that we can define the intensity as V star t Vt, and if we just do it again, this we did it last time, that's how it expands. This quantity is the intensity. So we have first term, second term, and the third and fourth. So first term is basically the intensity coming from this point at t minus t1. This k1 is a factor by which the field gets attenuated because of the different this reflection, and sorry, the splitting here and the splitting here. Similarly, it minus t2 is the intensity coming from this point t minus t2, and then this is the cross term and its complex conjugate. So let me mention that if we just open up the first path t1 and close this one, then this is the only term that we are going to see. If we block this path and then keep only this path, then that is the term that we are going to see here. But if we open up both the paths, then we not only see this term and this term, but we'll also see these cross terms. And now the point to the point to note here is that we can always measure the intensity that is coming out of the source, but if we ask this question as to what is the correlation between the field points in that source, that we cannot directly measure. So for that, we make an interferometer and measure the intensity here, and we find that the intensity measurement at this point t actually contains this cross correlation function, and then today we will see how to extract this cross correlation function through this intensity measurement, and to what extent and in what situations we can extract that information. So that is what we are going to do today. Okay, so that is the intensity at the output port of the interferometer that we see, and this is basically our general temporal interference law. And the essential point is that the intensity measurement at the detector yields the information about the correlation function. That means that is this. Now we can just simplify this a little bit, and so this is k1 k2. So now we can write this k1 k2. This k1 k2 we can write as these are k1 k2 are in general complex numbers. So we can write k1 k2 e to the I phi k. So that's how we write k1, k2. Now this gamma that can be actually be written in the following way, which kind of simplifies things a lot. So gamma t minus t1 t minus t2 this is divided by this quantity I t minus t1 and I t minus t2, and these are the intensities coming from the if only upper or lower arms of the interferometer were open and the other one was closed. So let's also multiply this with the same quantity so that it is I t minus t1 okay. Now we see that this quantity is essentially the degree of second order coherence. So we can write this with this period last time. So this then is basically equal to I t minus t1 I t minus t2, and then this is the complex degree of coherence function gamma t minus t1 t minus t2. Okay, so this is the complex degree of coherence function. We can take its mod, the absolute value, and then it also gives us e to the I argument of gamma. That's the mod of gamma, and that's the argument of gamma. So if we write it in this manner, then we can write this interference it just as first term, second term, and this term I am writing k1, k2 as this gamma cross correlation function in terms of the degree of coherence. And so if we combine this, the complex conjugate part, we have this cosine argument of y plus phi k. So this is how we can rewrite this one. Okay. Now this is the interference, or this is the intensity that we observe at the output of the interferometer. Now there is a very useful concept in studying interference and interferometer, that is called the visibility of the interference pattern, because we see this is a cosine term. That means the intensity will change periodically. So there will be a maximum, there will be a minimum. So one can use that maximum value of intensity and then the minimum value of intensity to define this quantity called the visibility. So V equal to I max minus I min divided by I max plus I min. And if we just do the math correctly, one can actually show that this quantity is just this term twice k1 k2 and divided by in fact this term. So that is the visibility. Now in situations when the intensity coming from the upper arm of the interferometer, or one of the arm of the interferometer, is same as the intensity coming from the second arm. That means this k1 square IT minus T1 is equal to k2 square IT minus T2. So when these two terms are equal, it turns out that this visibility is simply equal to this degree of coherence function. So we see that this is a very easily experimentally measurable quantity. I mean, one measures the intensity, the maximum value of intensity, minimum value of intensity, and that is the visibility. And it turns out that visibility is basically equal to the degree of coherence function when these two quantities are equal, and it is proportional even when these two are not equal. So that this is a way of this visibility is the way of measuring the degree of coherence function. We'll also see eventually how to measure the argument of gamma, but this is how we measure the degree. Okay. Now This is again the generic interference law. We've seen that we can write this in terms of the degree of coherence function, and the visibility can give us the the degree of the coherence function. Now, in general, it is not very easy to find this measure this correlation function. So we'll categorize the situations in which one can actually measure this coherence function easily, and in which case it cannot be measured that easily. And for that purpose, let's just remind ourselves that this cross correlation function is actually connected to this cross spectral density function through this generalized Wiener-Khintchine theorem. And this cross spectral density function, in fact, can be we can have three different cases of looking at this cross correlation function. And in fact, that strategy, this strategy of dividing the type of cross correlation cross spectral density function will let us choose what measurement strategy we should have for this cross correlation function. So let's look at the first case, which is when there is no correlation between different frequency components. That means when this cross spectral density function is of this form, that this omega w omega 1 omega 2 is of the form that is s of omega some spectral density function times the Dirac delta function delta omega 1 minus omega 2. So this says that if omega 1 is not equal to omega 2, then this cross spectral this cross spectral density function is essentially 0. This cross spectral density function is non-zero only when omega is equal to omega 2. That means it's the same frequency. So this basically means there's no correlation between different frequency components. So if that is the case, we have seen that this is basically the case of stationary random process. I mean, we looked at if the process is stationary random process, then we last time we had seen that the cross spectral density function assumes this form. So then that indeed is our first case here, is that when the cross spectral density function is of this form, that means which has no correlation between different frequency component. So in this case, we find that since this is it's a stationary random process, that means we know that the correlation functions cannot depend on the origin of time. And so in this case, this I t minus t1 that we have this will simply be I0, which is basically saying that it is time independent. The intensity doesn't depend on time. Similarly, I t minus t2 is also independent of time, and then the correlation function gamma t minus t1 t minus t2, this depends only on the time difference, and so it is just a function of tau, where tau is t2 minus t1. We can also look at the degree of coherence function gamma tau, and this is then simply, well, the mod of it is gamma tau divided by the intensity. So if we substitute these, we can see that we can write this intensity as just k1 square I, k2 square I. I'm writing for I naught, I'm just writing I, this 2 k1 k2 I, this gamma tau. So what we see here is that now this intensity is no longer dependent on time. So what we see at the end of the interferometer, it is stationary, it doesn't change as a function of time. So and this intensity through this intensity measurement, then one can actually find this gamma of tau. Okay, so this is what we get, that the intensity at the output of the interferometer is independent of time, and this is how it's connected with the degree of coherence function, and for this particular case. Now when we go to the second case, which is basically perfect correlation between different frequency components, this is the exact opposite of the first one. So in this case, the cross spectral density function, which is defined as the ensemble average of this quantity, is same as the quantity itself. So the ensemble average doesn't bring in anything. So essentially they're saying there's really no randomness in the process. The frequencies are perfectly correlated, so there's no randomness, hence the ensemble average is same as the quantity itself. So that's the case when there's a perfect correlation. Now in this case, we have to, if we look at the all these quantities, then we find that the correlation function in this case, T1, T2, which is defined as V star T1 V T2. This quantity, which is ensemble average, that will actually become independent of this ensemble average, and this is simply V star T1 V T2. Okay, and we can also write this then as product of two integral minus infinity to infinity. V star we can write as V tilde star omega 1 e to the plus I omega 1 T1 plus, because this is a star, d omega 1 times minus infinity to infinity V tilde omega 2 e to the minus I omega 2 T2 d omega 2. So that's how we can write this the cross correlation function. Now the intensities in this case, and in fact intensity is defined as IT1. So we could just do IT, which is essentially gamma of T and T. And so this essentially we can we see the form of this one. So this is essentially the mod square of this quantity, which is simply minus infinity to infinity V star omega V tilde omega e to the minus I omega t d omega. Okay, so we see that the intensity in this case actually does depend on time. So it is not stationary, it is not time independent, and of course the cross correlation function depends on both the time arguments T1 and T2. And in fact, we can also, if we look at the degree of coherence function, that means gamma, small gamma T1 T2. So since there is a perfect correlation in frequency, we will expect perfect correlation in time as well. But let's see if we can get it. So this is defined as gamma. In fact, we look at the mod of this as a degree, and so that's gamma T1 T2 divided by the two intensities, which is I T1 and I T2. Okay, this we can also write as mod square of this one, and we can take the square root. And if we do this, we can also show that this is essentially and here we have and since perfect correlation, this is essentially V star T1, V T2 mod square divided by V star T1 V T1 V star T2 V T2. And if we write it this way, we can see that this quantity is essentially equal to 1. So, the degree of coherence, degree of temporal coherence, that is 1 when there is perfect correlation between different frequency components. Okay. So, now in this case, since both the intensity depends on time and the intensity depends on time and also the cross correlation function depends on both the time arguments, we no longer have this intensity at the end of the interferometer being independent of time. So, it still does depend on time, but we do have these properties that we can utilize when studying and quantifying the correlation function in this case. Okay, so these are the two extreme cases when the frequencies are perfectly correlated and frequencies are completely uncorrelated. But we can have intermediate case when different frequencies are partially correlated. This is a vast topic. I am actually not going to go into it, but I will just show one example of such case. So, for example, if the cross spectral density function, which is defined as this, has this functional form, then we can see this actually represents the correlation of every type. If we take one extreme, that means if we take this, this is a Gaussian function, and this is also kind of a Gaussian function. This is a double Gaussian. So, if we take the limit this omega c going to 0, then this essentially takes this form, because with omega c being 0, this is essentially a delta function. Right. So, yeah, so this is essentially a delta function. So, this assumes this form, and then we can write this as this is the spectral density, and that's a delta function. So, this is our case 1 when there was no correlation between different frequencies. If we take another limit that omega c going to infinity, in this case we can see that this term is actually just 1, and this is what we are left with. We can actually write this as as a product of two terms, and this is basically the complex conjugate. We can write this in this case it does not really matter, but then this is simply written as a product, which is V star omega 1 V omega 2. So, this is the case of perfect frequency correlation between different frequencies. So, I am not going to go into the details of this one, but this I am just showing as an example of the cross spectral density function, one extreme of which is the no correlation between different frequencies case, and the other extreme is the perfect correlation between different frequencies. Okay. Now, let us look at now to get more intuition about these things. We will look at one case where we can see things with some intuition. So, let us look at a case when the field is stationary, quasi-monochromatic, and has a Gaussian spectrum. So, what do these things mean? We of course know this when stationarity means that the cross spectral density function has this functional form, and in that case we can write the intensity at the output port of the interferometer in this form. Next is quasi-monochromaticity. So, quasi-monochromatic spectrum means that the width of the bandwidth of the spectrum has to be less than the central frequency. So, this means that if we just represent this spectral density as a function of omega frequency, let us say if this functional form looks something like this. This we can call the mean frequency omega naught, and this is the width of the cross spectral density function. So, in this example we see the delta omega is definitely much smaller than this the mean, the omega naught, and this is what we mean by field being quasi monochromatic. So, that is our second condition, the field should be quasi monochromatic. That means delta omega should be much smaller than the mean frequency. Now, in this case our Wiener-Khintchine theorem, which is gamma tau in terms of the spectral density, this we can write by substituting omega as omega naught plus omega 2. This we can simply write this as S in this form, where we are substituting for omega, we are substituting omega naught plus omega 2. So, these limits go to minus infinity minus omega naught, infinity minus omega naught, and then for this omega we substitute this and then this. Now, we can separate this e to the minus I omega naught tau from here. It comes out since it is quasi monochromatic, then this is essentially does not really matter, because this is this quantity is same as minus infinity to an infinity. That is the approximation we have, and then we can just, instead of omega 2, we can just write this in terms of omega as a simple integral. Now, the next is that it is a Gaussian spectrum. So, if we put in the Gaussian spectrum, and let us assume this is the normalized Gaussian spectrum, where the spectral density S omega has this form and delta omega is its width, and this is normalized, and in this case if we just use this integral for calculating gamma tau, we have this form for gamma tau, where tau c is just 1 over delta omega. So, this is just one example of a spectrum which is quasi monochromatic, and as well as a Gaussian spectral Gaussian functional form, and in that case we see that this autocorrelation function has this nice form. Okay. Now, so for this one, this particular example function, we can actually write the intensity expression, the intensity at the output port of the interferometer as this, and this is the degree of coherence function, and that's our cosine function. Now, at this point I just want to kind of have some intuitive pictorial understanding about coherence. So, we'll just try to simulate this simple case and understand all these concepts of the spectral width and this tau c that we will define as a coherence time and so on. So let's have a visualization of this. So, here I am just it's the same thing, that's the same spectrum I have. This is the mathematic I am using, the Wolfram cloud. So, this is the spectral density, that is a form, and for the spectral density the degree of coherence function has this form, and then we can write the intensity at the output port of the interferometer by this expression. And now I have just written a program here, a simple program to actually simulate the intensity, and then I am plotting it as a function of this tau, that is the time difference, and there are different parameters that I can actually vary. So, let us just take a look at this. Okay, let us make it a little bigger. Okay. So, here are 3 knobs that I have, and then that we can use to change. So, this is the mean frequency. Let us put the mean frequency that is smaller than much larger than delta omega, and this k1 is basically the splitting constant from the beam splitter. So, as we see, if we change the mean frequency, this, and here I am plotting, this is the spectral density, and that is the degree of temporal coherence function, and this is the intensity at the output of the interferometer. So here this is tau, very tiny, probably you can't see it, hopefully you can. So here this is the intensity as a function of tau. So if as we see, if we increase tau, we see this sinusoidal variation in intensity, and then we see this overall decrease in the visibility of the interference pattern. And if we decrease omega naught, of course we have a spectral density that is centered at a different frequency, but since this is a smaller frequency now, we see the fringe period has become larger. So mean frequency basically decides, mean frequency of the spectrum basically decides what will be the fringe period of the interference pattern, interference fringes that we will see at the output port of the interferometer. Okay, so let's keep it here. Now this is the width of the spectrum, delta omega. So delta omega decides this width of the spectrum, and this is the degree of temporal coherence function, and we know that these two are connected. So if we increase delta omega, this will become broader, yeah, and this will become narrower, and this is simply, this one is simply the degree of coherence function multiplied by a cosine function. So when the width of this one decreases, width of this one will decrease as well. So this one is just the envelope function that one has here. Let's increase the delta omega further. This will become even broader, and this becomes narrower. Let's increase the frequency a little bit more. And now we see that the fringe period has become smaller. Let's increase some more the width. Yeah, and it just becomes broader and more and more narrower. In fact, when this width is very tiny, in fact, we can see the numbers as well. When the width is very small, this is like just very few frequencies, and in that case, the degree of temporal coherence function becomes really large. And so when if you go to the limit of really monochromatic frequency, then this will just become a flat line. That means the degree of coherence is basically 1 for any separation tau. Okay, so that's what omega naught and delta omega they do. We also look at what this K1, that is the splitting ratio, that one does. So here I have K1 equal to 0.07. This is a situation when both are equal. The intensity coming from both arms of the interferometer equal, and in that case we see the visibility is 100%, and this we can see the minimum is going all the way down to 0. But if we change the value of K1, so this K1 is -7, this one, so that K1 square, which is the quantity that shows over here, is basically half. So now if we increase K1, then there is a misbalance between the intensity in the arm 1 and arm 2, and then that will cause the reduction in the visibility. So the minimum won't go all the way up to 0. So let's increase it a little bit more, then we can see it a little more dramatic effect. Yes, now visibility has gone down because the minimum is not going all the way down to 0. Let's increase it even further. So all this does is reduces the visibility, and in the event when this becomes K1 actually becomes 1, that means all the intensity is coming from just one arm, then the intensity will just be flat, we will see no interference. So in order to see interference, we have to have something coming from both the arms of the interferometer. Okay, so this is just for the kind of intuitive understanding of these essential concept involved with coherence. Now let's go back to the presentation. We now look at the concepts of coherence time and frequency bandwidth, which are very useful concept in the context of stationary random process. So coherence time is defined as the second moment of this quantity, and the frequency bandwidth is defined as the second moment of this quantity. And in fact, this coherence time delta tau times delta omega, this is actually has to be greater than 1/2. That's more like uncertainty type relation that we actually see here. Now let's just look at in the Gaussian spectrum that we just had. For this, the correlation function had this form, and the degree of correlation function has this form. So for this Gaussian spectrum, the spectral density is this, and this was our degree of coherence function. So this quantity, the half width, is here is the frequency bandwidth that we have, and the half width over here is our coherence time for this particular spectrum. So for this spectrum, we can very nicely define the coherence time and also the frequency bandwidth. And here I am actually I have listed a few well-known sources. So it's a very well stabilized laser, diode laser, which are not that stabilized, and then sunlight. And these are the numbers that we have for frequency bandwidth and coherence time. So for very stabilized laser, the frequency bandwidth of the spectrum is of the order of 10 to the 6 hertz, is 1 megahertz, and the corresponding coherence time is 10 to the minus 6. So if you think in terms of length, which is speed of light times the coherence time, this is about 300 meters. So if it's a field coming from the well stabilized laser, if you choose 2 points that are 300 meters apart, they will still be coherent. Now in diode lasers, the frequency bandwidth is about, let's say, 1 gigahertz, and then the coherence time is in nanosecond, and in there we find that the coherence length is of the order of 0.3 meters. For sunlight, the frequency bandwidth can go up to 100 terahertz, 10 to the 14 hertz, and the coherence time is 10 to the minus 14 second, and the coherence length is of the order of 3 micron. So even in the sunlight, if you choose 2 points that are separated by not more than 3 micron, we will still see interference. So if you have a sunlight going through an interferometer, a Mach interferometer, in which the path length separation is less than 3 micron, we will actually see interference. Okay, so that's the concept of coherence time and frequency bandwidth. These are very useful concepts, but I think one thing one has to be very careful that this concept is useful only when the spectral density is singly peaked. If this is a singly peaked function, it is always easy to define the second moment and variance and all. But if the spectrum is multiply peaked, the concept of coherence time and frequency bandwidth cannot be defined in the usual sense of an RMS width. So for example, if let's take the for example, if the spectral density is of this form, that it has one peak like this, the other peak like that. So it has all the frequencies in this region, all the frequencies in this region, but these frequencies are missing. So you can also have the sources that are multiply peaked in the in their spectral density, and in that case, you may have the spectrum or the correlation function, or rather the degree of coherence function. If you look at it may have a function form like this. Okay. So what we are seeing here for such spectrum, we can have a degree of coherence function which is again multiply peaked, and now we see that this degree of coherence function becomes 0 at this point for this toss separation, and it again increases and then becomes 0, increases again, becomes 0. So if we choose 2 points in the field that are separated by let's say this much time separation tau, then we find that these two fields are very nicely correlated because the degree of coherence function is this. But if we choose 2 points in the field that are separated by this much of time separation, then we find that those 2 points are those 2 time points are completely incoherent. But again, if we choose a point that is that the pair of points that are separated by this much time separation, then these 2 points will again become coherent. So for such functions, one cannot define the width of the function, and hence it is difficult to define the coherence time in the sense that we do over here. So one has to be careful in this when the spectrum is multiply peaked. One has to be careful as to defining the concept of coherence time and frequency bandwidth. But one has to kind of understand that here one is talking about the coherence or the degree of correlation between the pair of points depending upon their separation. For some separation it can actually become 0, but for another separation which is larger than the first one, it can actually become a positive again. Okay, so this is all we have for today. Thank you.